Hi guys, and welcome to the final video on Unit 18, further hypothesis testing. After this video, if you make sure you're happy with the content in Unit 18, and then move on to completing past papers, which we will then use as further evidence for our predicted grades. An email will come out with a bit more information on that, or I'll put something on Show My Homework. But the focus for now should be on getting to grips with this last part of Unit 18. So as always, there's a starter to have a go at. So pause the video here and then try these two questions. Okay, so we're told in question 1 that the weight of beans in a tin has a normal distribution with a mean of 415 grams and a standard deviation of 3.4 grams. We want the probability that a randomly selected tin of beans has a weight less than 409 grams. So you're going to go to normal cumulative distribution on your calculator. Your upper bound is going to be 409 grams. Your lower bound is going to be 0, or a very small number. And you're going to put in the mean of 415 and the standard deviation of 3.4. And hopefully you should get this probability equal to 0.0388 to 3 significant figures. Next up, company suspects that the mean weight of tins is lower than it should be. Write down the company's null and alternative hypothesis. So the null hypothesis, remember that's the status quo option. So that's going to be that the mean remains at 415 grams. And the alternative hypothesis, H1, is going to be that the mean is lower than a 415 grams. So you should have something like this: H0 mu equal to 415, H1 mu less than 415. Then we're told that a sample of 20 tins is taken and the mean weight of those tins is found to be 413 grams. Okay, so we know that the sample mean is also normally distributed. It has the same mean as the population of data, but its standard deviation is going to be equal to its variance is going to be equal to 3.4 squared divided by the sample size, so that's divided by 20. And we want to carry out a test at the 1% significance level to see if there is evidence that the machines are indeed producing tins with a mean less than 415 grams. So, X bar, that's our sample mean, has a normal distribution with mu 415 and variance 3.4 squared over 20. And because what we're interested in is whether the mean is less than 415, we're looking for evidence at this end of the normal distribution. So we find out what's the chances of getting a mean of 413 grams or something more extreme, and that's equal to 0.00426. Okay, and because this probability is less than the 1% that we're testing against, then what we say is that there is evidence at the 1% level to suggest that we can reject the null hypothesis. I would go with that language rather than talking about accepting the alternative hypothesis, okay? So go with that language of there's evidence at the 1% level to reject the null hypothesis. Okay, next up, we're told that a bus journey from Leeds to London is normally distributed with a mean of 220 minutes and a standard deviation of 8 minutes. Find the probability of a bus taking longer than 235 minutes. So similar to the first, you're going to go to your normal cumulative distribution, give a mean of 220, a variance or standard deviation of 8 minutes, sorry. And then your lower bound is going to be 235 and your upper bound is going to be some big number of your choice. And you should get that the probability that x is bigger than 235 is 0.0304. Okay, next up, the bus company suspect that the mean bus time has changed in some way. Write down a null and alternative hypothesis for a two-tailed test. Okay, so our null hypothesis is that the mean remains as it's been, 220. And the alternative hypothesis this time, well, we think the mean bus time has changed. We don't know whether it's gone up or down. So it's just going to be that the mean is not equal to 220. And then we take a sample of 10 bus journeys and find that they have a mean time of 230 minutes. Test at the 1% significance level whether there is evidence that the mean time has changed. Okay, so this sample and the sample mean is going to be normally distributed, and it's going to have a mu equal to the population mean. So it's going to have a mean of 220, but its variance is going to be 8 squared divided by the sample size, which is 10. Okay, this time it's a two-tailed test at the 1% level. So remember, we're splitting for our significance level or our critical region. We're splitting 0.5% here at the top end of the tail, and 0.5% at the bottom end of the tail. Okay, so we're interested in whether our sample mean lies within one of these critical regions. And in this case, our sample mean is 230, which is bigger than our population mean. So we're interested in working out the population of getting 230 minutes as our journey time, or something more extreme. And we find that that is equal to 0.000386, which is less than 0.5%. And so we have evidence to reject the null hypothesis. Okay, again, I would use that language rather than the language that's given here. Now, in the textbook, you might have seen there was a question about calculating the p-value for a two-tailed test. Now, strictly, the p-value is going to be 2 times this number here. So we're interested in the probabilities of our event happening at the top end of the distribution or at the bottom end of the distribution. Okay, so the p-value strictly for a two-tailed test would be 2 times this number. And then we would compare the p-value to the total significance level. So we would compare that against 1% rather than comparing it against 0.5%. Email me if you want any more detail on that. Okay, so for today's lesson, we're looking back at R, which is Pearson's product moment correlation coefficient, or what I'll describe it as for the rest of the day, PMCC. So you might remember this, and it's a way of measuring the level of correlation between two variables. So if we have R equal to 1, which is the maximum value that R can take, then we have this situation where we have perfect positive correlation. The lowest value that R can take is -1. And that occurs when we have this situation. So we have perfect negative correlation. And then everything is on a sliding scale from here down to 0 in the middle, which means we have no correlation. And there's a nice video here which shows you how to calculate R for a sample set of data on your class whiz, and also gives you a bit more background on what the PMCC is. Yeah, it's worth having a look so that you know how to calculate R on your class whiz. Now, for hypothesis testing, we need to introduce a new element, which is called rho, another Greek letter. And rho represents the PMCC for a whole population of data. And that's contrasted with R, which is our PMCC for a sample of data. Okay, so rho is what we're calling the correlation coefficient for a whole population of data, and R is the correlation coefficient for a sample of that data. And remember, R is on a scale from -1 up to 1. Perfect negative correlation on a scale up to perfect positive correlation. And there's a nice video here which runs you through these two ideas and gives you some nice examples, so well worth checking out that link at the bottom there. Okay, so then if we want to move on to hypothesis testing for the correlation coefficient, we start from the null hypothesis. So the status quo position to start from is that there is no correlation in the population. So our starting point is that rho is equal to 0. For our alternative hypothesis, that depends on whether we're looking for evidence of positive correlation between the two variables, negative correlation, or correlation in either direction. So our alternative hypothesis could be that rho is bigger than 0. So that's if we're looking for evidence of positive correlation and is looking at the top end or one tail of the test. Our alternative hypothesis could be that rho is less than 0. So that's considering whether we've got negative correlation. And again, that's going to be looking at the bottom tail of the test. Or our alternative hypothesis is that rho is just not equal to 0. So there is some form of correlation. And again, in that case, we're interested in doing a two-tailed test. So, once we've defined our null hypothesis and our alternative hypothesis, we then pull out a sample of data of size n from the population, and we find the PMCC R for that sample. So in this case, I've imagined pulling out a sample of data and finding that the PMCC is equal to minus 0.67. We're then going to compare that R value against a critical value based on the sample size n and the significance level we want to test against. So essentially what you'll find, and this is on page 545 of your textbook, is a table which tells you, given a particular sample size, so this is our sample size n down here, for you to have evidence of correlation, then we need to have an R value of 0.3009 if we're looking for confidence at the 5% level, 0.355 if we're looking for confidence at the 2.5% level, 0.4105 if we're looking for confidence at the 1% level, and if we're looking for confidence at the 0.5% level, we're looking for R value of 0.4554. Okay, so as the sample grows in size, so as the sample gets bigger, and as the level of the significance level reduces in size, so you're looking for a greater degree of confidence. As the sample increases in size, then you need a lower value of R to show that there's some evidence of correlation. And as the significance level decreases in size, then you need a higher value of R. Okay, because the more confident you are that there's correlation, the greater the R value needs to be. And the greater the sample size is going to be, the smaller the R value that is required. Hope that makes sense. So two things that affect the size of the critical value. So let's imagine we've taken a sample of 31 pieces of data, and we want to test for negative correlation at the 1% level. So we're doing a negative correlation check, so this is a one-tailed test, and we're interested in looking at it for the 1% level, so we want evidence significant at the 1% level, and our sample size is 31. Well, the critical value at that level is going to be 0.4156. Now this is given to us as a positive value, but we've again got symmetry here, so the critical value in the negative direction is going to be negative 0.4156. And because our R value is more negative than that, then we have evidence significant at the 1% level to reject the null hypothesis. So we're starting to see evidence that there is a negative correlation between these two variables. Now in the book what they do is they take the modulus of our R value and just compare that with the value in the tables. That does exactly the same thing. Okay, and this is what the table looks like on page 545. So to finish up today, I'm going to look at one example and then set you down to work. So in this example, we're told that the amount spent by a government on unemployment support is expected to be negatively correlated with the amount spent on education. Data are collected across 50 countries in 2016. what is the population associated with this sample? Well, the population is going to be every country, all countries globally in 2016. Okay, and our sample is the data just for 50 countries in 2016. So all countries in 2016 is our population, and our sample set is 50 countries in 2016. Write down an appropriate null and alternative hypothesis. Okay, so the null, the status quo option, is always that there's zero correlation, so that there's no correlation between unemployment support and the amount spent on education. And here our alternative hypothesis is that there is negative correlation, so that rho is less than 0. So our null hypothesis is that rho is equal to 0, and our alternative hypothesis is that rho is less than 0. Now for our sample, so we have, and then we're asked to perform, what were we told? We're told that the sample correlation coefficient is found to be negative 0.36. So for our sample of 50 countries, our R value is negative 0.36. What is the conclusion of the hypothesis test at 5% significance? Okay, so we know our R value is negative 0.36, and what we need to look for now is we need to look at the tables and look at a sample of 50, so n equal to 50, and a one-tailed test at the 5% level. So let's see, it might be hard to see from this table, but if we go to 50, and we're interested in a 5% significance level, you can possibly see there that that value is 0.2353. Okay, so our critical value is 0.2353. Now, if you like, you can think of that as negative 0.2353, and our R value is more negative that, so it's closer to net positive to perfect negative correlation. Or you can think that the modulus of our R value, which is the modulus of negative 0.36, that is bigger than 0.2353. And so we have evidence at the 5% significance level to reject the null hypothesis. Okay, I hope that helps. Please go on now and try exercise 18C and mixed practice 18, and email me with any questions you might have. Alright guys, take care out there. Speak to you soon.